Hi, welcome back to my summary of the Feynman Lectures. This is Volume 1, Chapter 2. This chapter is called Basic Physics, and he starts off this chapter by asking you to imagine yourself sitting at the beach and looking out at the sand, and thinking to yourself, is the sand the same as the rocks that you see laying in the sand? And then looking up into the sky at the moon and wondering to yourself, is the moon the same as the rocks? Meaning, are the rocks just big pieces of sand, and is the moon really just a big rock? Because if those two statements are true, then it means that the world is much simpler than it appears at first glance, and there's less to study. You can study one concept and understand the sand, the rocks, and the moon. And this amalgamation process is something that physicists have been doing throughout history. And Feynman gives an example of this, which is kinetic energy and heat. Everything is made of atoms. Atoms are always moving. Atoms have kinetic energy, and what we see macroscopically as heat is really just the aggregate kinetic energy of all of the atoms in a system. So heat and kinetic energy are amalgamated into one concept. We only have one concept to study at a fundamental level. When it actually comes to application, that's not true. But when it comes to understanding how the universe works, it is. Another famous example of this is James Clerk Maxwell unifying electricity, magnetism, and light, showing that electricity and magnetism are really just two parts of one thing, which is electromagnetism, and that light is electromagnetism. And they're all just different varieties of one thing to study, and it simplifies the universe. The next thing that he talks about is electrical charge, and I just want you to imagine a positive charge right here and a negative charge right here. And you can think about this kind of like the positively charged nucleus of an atom and the negatively charged electron shell near it. And these two particles are very close to each other. We have another negatively charged particle that's all the way over here, very far away, not drawn to scale. These are much closer than they appear. This is much farther away than it appears. The point being that these are much closer to each other than either of them are to this particle. As you know, with charged particles, likes repel and unlikes attract. So this particle is repelling the negative over here, and it's attracted to the positive over here. But from the perspective of this particle, it's so far away from either of these, and they're so close together that this is like one particle to this particle. And the positive and negative are balancing each other out. So from the perspective of this particle, because it can't tell the difference between these two, they're too close together, it's too far away to distinguish, it looks like one blob of charge that's, or not charge, it's neutral. Another way of thinking about it would be, which is closer to the truth, is that this particle is being influenced by both of these, but the effects are just canceling each other out. Just like in the last video, our example of the glass of water, where we don't, it's a closed system, there is no way for the water to escape, and we don't see the water level changing over time, but really it's evaporating and returning to the liquid form, just in both directions at the same rate. So from the outside, macroscopically, we cannot distinguish that this is happening, but there is that dynamic process going on. Here, this particle is being influenced by both of these particles just in an equal and opposite measure, so we can't distinguish the difference from the outside. He brings up the point that in an atom, you have a positively charged nucleus, and you have negatively charged electrons on the outside. And he says how there's so much space between this positively charged nucleus and the electrons orbiting it. That's not really a good way to put it, but for now we'll put it that way. That if you were to take an atom at its normal size, its unbelievably tiny size, and blow it up to about the size of a large living room, that the nucleus would then be the size of a speck on the wall that's just barely visible. that is how tiny the nucleus is compared to the total space that the atom occupies, and that's how far away from the nucleus these electrons in the electron shells are. And that could lead you to wonder, if the positive and negative are attracted to each other, why don't the electrons just fall all the way in to the nucleus until they're on top of each other? And physicists used to think that the nucleus was large, and that was how it worked, that most of the space that the atom occupied was the nucleus. But then we found out that the nucleus was tiny and the atom was mostly empty space, so it led to a lot of questions. And the answer lies in Heisenberg's uncertainty principle, which is that I'll separate this off, what I drew over here, that the uncertainty in x times the uncertainty and momentum is equal to h bar over 2. And you don't have to worry about what this constant means right now, but just know that it's a constant. So if your uncertainty in x is going to decrease and this constant's going to stay the same, that means that your uncertainty in momentum has to increase, and vice versa. So if the electrons got closer and closer and closer to this nucleus and kept having less space that they could end up being in, that means that there would be less and less uncertainty in x, meaning you would need to have more and more uncertainty in momentum. And if your uncertainty in x were to ever reach 0, if the electron was ever completely still, or we had full knowledge of its location because it was right on top of the nucleus, then the momentum would have to be infinity, which is obviously impossible. And this might not make sense to you because you're going to ask yourself, well, so does Heisenberg's uncertainty principle just overrule the electromagnetic force? This doesn't make sense, and we're going to have to study quantum mechanics for it to make sense. Again, these first 3 chapters are not a deep dive. They're just an introduction to get you interested, but that is a brief explanation as to why the electrons and protons don't fall in towards each other, and the nucleus and the electrons don't fall in towards each other. The next thing he brings up is the difference between waves, fields, and particles, or lack thereof. And he asks you to imagine a cork floating in water with another cork right near it, and how if you push this cork in the water, that this cork over here will then get pushed by the water. If the water was completely still, nothing else is influencing these 2 corks besides you pushing one, then that water's influenced, it pushes the other one. And obviously, as you do this through different trials and start the corks farther apart, you'll notice less and less of an effect. And that's the same way an electromagnetic field works, or an analogy for an electromagnetic field, where if you imagined having a positively charged particle that's generating a field that's spreading out in all these different directions around it, that this field, if you place a negatively charged particle inside of it, that negatively charged particle is going to experience a force inward towards this positively charged particle, and vice versa. If it's a positively charged particle, it's going to experience a force away. And this field the cork example is an analogy for it. He then says, though, that just like if you take that cork in the water and you oscillate it quickly enough, you'll have waves form away from the water. And that is the same thing with this charge. If you were to take this charge and oscillate it in space quickly enough, then you would have waves propagating away from this charge. You wouldn't have a field surrounding the charge. And if you were to oscillate this quickly enough beyond that, then it would be like particles are flying away from it. And that, it doesn't mean that that's what's actually happening. It just means that the math becomes more accurate if we're representing it that way. So at low frequencies, fields are the most accurate way to represent things mathematically. As the frequency increases, waves become the most accurate way to represent it. And then as the frequency increases even further, then particles become the most accurate way to represent things mathematically. Again, I don't expect that to make total sense, especially when we're not actually doing any math and showing any of the equations involved, and that might lead to more questions than it does answers, but that's kind of the point of these couple of chapters. He says, this book was written in 1964, I believe, so this might be outdated information, but he says, I believe it's 10 to the 12th is the fastest frequency that's ever been measured directly, and that any frequency higher than that at the time of writing that's ever been measured has been indirectly, because we know particles, we can calculate the frequency of their oscillation based on their energy. The energy of particles that are moving, that are oscillating at greater frequencies than what we can measure directly, we can measure their energy and then calculate the frequency that they have to be oscillating using that energy, assuming that at frequencies greater than what we can measure directly, the rules stay the same. And that might be an outdated number, that 10 to the 12th, but I'm sure that the same concept still applies today. The last things that he talks about in this chapter are, well, actually, I want to give some examples of numbers real quick that he wrote. So, this is the frequency in hertz, and this is behavior. So 10 to the second to 10 to the second to 5 times 10 to the fifth is what he writes as the range where you get field behavior. And he calls this an electrical disturbance. And then he says that 5 times 10 to the fifth to 5 times 10 to the 15th is where you get the behavior of waves. And then 5 times 10 to the 15 to 10 to the 27th is where you get particle-like behavior. And you can look up the actual chart that he puts in the book. It's got a lot more subdivisions to this where it gives specific examples of what you'd be talking about. Breaking this up into all the different types of wave, or radio waves and light waves, and different types of particles. But I just wanted to throw this in here to give you some kind of numerical example of what I was talking about before, with the different frequencies of oscillation and the different behaviors that are represented, the different behaviors you would use to represent them mathematically. The last thing that he talks about in this chapter for the last couple pages, I'm going to pretty much skip over, which is he gets into particle physics, and he gets farther into quantum mechanics, and a lot of it is kind of outdated, and he basically goes through a list of particles that have been discovered that we're not really sure where they fit in, and unanswered questions in physics, but several of the things he brings up have been answered at this point, and some of the assumptions are now incorrect that he's making at the end of the chapter, after the past 60 years of research or so that's been done since then. So I'm going to end it here, and I'll see you guys next time.